Welcome to video number 9. Today we're going to talk about one of the most commonly encountered waveforms in electronic applications, the sinusoidal waveform. All right, a sine wave is a continuous periodic signal that's defined by the following equation. Now, lowercase italic v means it's an instantaneous value of a voltage in this case. And the t in parentheses is just function notation, meaning that this voltage is a function of time. And it's given by Vp, which is the peak amplitude of the sinusoid, times the sine of omega times t. Omega is the frequency of the sine wave in radians per second, and t is just our independent variable time. Now, we use radians per second because it's the best unit to use when doing calculus and things like that. But most of the time, we prefer to think about frequency in terms of cycles per second, which is hertz. We designate that with F. Omega, the radian frequency, is equal to 2 pi times the frequency in hertz. Omega equals 2 pi F. And similarly, frequency in hertz is equal to omega, radians per second, divided by 2 pi. The 2 pi comes from the fact that there are 2 pi radians in one complete cycle of a sine wave, or one rotation around the unit circle. Anyway, the period of the signal is the time interval between identical points on that signal, okay? Assuming that it is a periodic signal like a sine wave. All right, so we designate the period with a capital T, and frequency is the reciprocal of the period. The period is the reciprocal of the frequency. All right, down here at the bottom, I've been referencing this waveform, which is a sine wave. A sine begins at 0 and will increase and then decrease like that. This waveform is actually a cosine waveform, all right? It's like a sine wave that's phase shifted, but a cosine starts at its peak and then varies sinusoidally. But it's just like this, except shifted over. All right, let's do a couple of problems. All right, here I've got 4 waveforms, and what I want to do is determine the equation for each of these waveforms. All right, so to write the equation, we need to know the peak amplitude, which is given here by inspection for V3. V sub P equals 10 volts. The period of the signal, let's go from here to here, is 1, 2, 3, 4 milliseconds. 4 milliseconds. And that means the frequency is 1 over 4 milliseconds, which is 250 hertz. So this is a sine wave, 250 hertz, peak amplitude 10 volts. All right, we're going to write that as 10 sine 2 pi times 250 hertz times t. And I'm going to put that in parentheses just to emphasize we take the sine of that whole quantity there. And lastly, let's throw the units in. 10 sine 250t volts. Now, you could multiply 2 times 250 and write that as pi times 500, but I like to keep the 2 pi separate so that I can see, that's 250 hertz. Okay, so let's go on and do V4. All right, this one is 12 volts peak to peak. That means it's 6 volts peak. It's reaching 6 volts and minus 6 volts. And its period is 1 microsecond. So for this signal, we've got Vp equals 6 volts, T equals 1 microsecond, and the frequency then is 1 over 1 microsecond, which is 1 megahertz. And I'm going to express that as 10 to the 6th power hertz. Right? It's a little easier to write. So V4 then is equal to 6 It's a sine wave, sine 2 pi times 10 to the 6th t volts. All right, 2 pi times 1 million hertz times t. Okay, V5. Oh, this one's a little different. We've got a sine wave, but it's riding on a DC level, so it has a DC offset. Well, that's not really a problem. We can just tell by looking at this one that the DC level is 2 volts, and the peak amplitude of the sine wave is also 2 volts. So what we've got here is V sub DC equals 2 volts, VP equals 2 volts, and the period of the signal, in this case it's easiest to go from this trough to this one. We've got 1, 2, 3, 4 milliseconds. So the period is 4 milliseconds. That means the frequency, like the one above it, is 250 hertz. All right, so the equation for this one, we have to write the DC part and the AC part as 2 separate pieces. We'll start with the DC part. We've got 2 volts DC plus 2, and it's a sine wave because it's starting at 0 crossing, 2 sine 2 pi 250 t volts. So we just have a DC voltage plus a sine wave riding on top of it. Another example of superposition. All right, the last waveform, V sub 6. Well, it's got a period of 10 microseconds, so that's easy. Its peak amplitude is 5 volts, but this one is a cosine wave flipped over, so it's an inverted cosine. And, well, that's easy enough to account for. We're just going to write this equation as minus 5 cosine. Let's see, what is our frequency? Is 1 over 10 microseconds, which is 100,000 hertz. Okay, and I could write that as 10 to the 5th power, right? 10 to the 5th power hertz. So I'm going to write it that way to save writing. Cosine 2 pi 10 to the 5th times t volts. So there we are. That's an inverted cosine with an amplitude of 5 volts. Frequency is 10 to the 5th power, or 100 kilohertz. And the radian frequency is 2 pi times that. So there's the equation for this waveform. All right. Now, since we're talking about shifted sine waves, let's expand on that and look at the more general case of a phase-shifted sinusoid. All right, now, looking at the waveforms, the dashed waveform is our unshifted sine function, okay? It's starting at 0 crossing at t equals 0 and progressing from there. In this first example, we have what's called a leading phase shift, okay? That is, this solid waveform starts a little bit sooner in time. The time difference between 0 crossing at the start, I'm calling delta t. All right, so that's equivalent to a phase angle, a phase shift, and in degrees, it's given by this formula. Okay, the phase angle, the phase shift, is plus or minus delta t divided by the period times 360 degrees. All right, the generic equation for the phase-shifted sine wave is Vp sine omega t plus a phase angle. For a lagging phase angle, we just subtract phi. Okay, in this case, the actual waveform is lagging in time by delta t, so we would assign a negative sign on there. And the reference sine wave, of course, has a phase angle of 0. Okay. Now, let's do a couple example problems to solidify this, okay? You may want to take a screen capture of this to have the equation and the pictures of the waveforms handy. All right. First example, V sub 7. All right, we have a 1 millisecond time. Okay, so period is 1 millisecond. Frequency is 1 over t. That would be 1 kilohertz. All right, the peak amplitude is 2 volts. All right, and we've got a delta t of 100 microseconds. All right, we know that the phase angle, phi, is equal to plus or minus delta t over t times 360 degrees. Okay, so we've got delta t of 100 microseconds divided by a period of 1 millisecond. And if I get my trusty TI-68 out here, delta t 100 microseconds divided by 1 millisecond is 0.1 times 360 is 36 degrees. So here we have a leading phase angle of 36 degrees. So V7 would be written as 2 sine 2 pi 1000 t plus 36 degrees volts. So we have a sine wave with a positive 36 degree phase shift. Okay, the next waveform, well, let's do the easy stuff. VP is 500 millivolts. F equals 100 hertz. So T is 1 over F, so that would be, what, 10 milliseconds, right? 1 over 100 hertz is 10 milliseconds. And let's see, our delta T is 850 microseconds. All right, so our phase angle for this one, and it is lagging, is delta T over T times 360 degrees is 850 microseconds divided by 10 milliseconds times 360 degrees. Let's see what we get for this one. 850 micro divided by 10 milli times 360 is 30.6 degrees, but it's lagging. So I'm going to call that minus 30.6 degrees. And our equation then is V8 equals 500 sine 2 pi, 100 t minus 30.6 degrees volts. So there we go. There are two examples of waveforms where we had to calculate the phase angle. A case where you would run into something like this might be the output of a filter circuit, which is phase shifted some amount relative to the input. A low-pass filter would give a lagging phase shift. A high-pass filter would give a leading phase shift. We'll talk about that stuff in a future video. And finally, to wrap this one up, let's talk about the root mean square value of a sine wave. We usually just call it the RMS value, and it's the equivalent DC voltage that would cause the same power dissipation as that sine wave in a resistive load. Okay? For a purely sinusoidal voltage or current, the RMS value is the peak value divided by the square root of 2. So whether it's a voltage or a current, we divide the peak by the square root of 2, and we've got the RMS value. And we can rearrange that to solve for the peak value. Given the RMS value, we just multiply by the square root of 2. And in general, the root mean square value for any periodic function, in this case I'll use a voltage, is given by this kind of messy bit of calculus where we've got the square root of the period of the signal times the integral from 0 to t, that is over one cycle, times the function squared with respect to time. That's our variable of integration, and that can be used for sine waves, triangle waves, square waves, any arbitrary periodic function. And again, we'll talk more about this stuff in a future video as well. But hopefully you got something out of this, and I will see you in the next video.